Hello. Good evening, everyone. Am I audible?
Yes, audible.
आवाज आ रही है?
Yes.
एक मिनट. Hello. So my, please, am I audible? Everyone?
Yes.
Yes.
Okay. 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 Is it visible?
Yes.
Yes.
Nice. So today we are going to learn about dynamic programming. In short, we say it as DP. So, anyone of you have any idea about what's dynamic programming and why it is so popular and it is widely used over everywhere? किसी को पता है?
It is a methodology of coding in which we uh, stop the problem in recursion of overlapping subproblems. We store the solutions of each smaller subproblem while solving it so that we do not need to recompute it again in the entire recursive process.
Yeah, I think that was a definition. Anyone else? Okay, I will proceed. So today, what topics are we going to cover? First, I will give you what's introduction, the basic idea, and then we will cover two topics about it. The first one is subsequence DP, and then substring DP, which basically deals with strings. This one. So, introduction to DP. So, what is that? Just a second. A method to solve problem by breaking them into smaller overlapping subproblems stores or memoizes solution of subproblem to avoid redundant work. That's what he said. That we break the problem into smaller subproblems like we did in recursion backtracking. But there's an extra catch. We are storing our subproblems which we calculated way before into our cache, and we will use it in future if it is required. So here we are reducing our redundant work. Just a second. Sorry for interruption. So yeah, where was I? Yeah. So here the basic extra thing with recursion is here we are storing our pre-calculated results so that we don't redo it again and again. Because sometimes in, for example, today you have learned about Fibonacci numbers, right, in the morning session. So so there we saw that the time complexity was going to exponential. Like we again and again we were calculating that result that we have calculated in past. So it But using DP, we can trim down the time complexity to linear. How can we do it? Let's go and watch. So there are some steps. With example and steps, I will show you how can you use DP. It's almost like recursion only, but there are some extra steps. So step number one, define a state function. So, for example, here I'm making fib of n. Fib of n, what does that mean? that fib of n will simply return me the nth Fibonacci number. Okay, that's for just abstract meaning for understanding. Then again, then next step we have to create our cache where we are storing our result. It can be map, set, vector, array, whatever you want to use. I am using a vector here, it's more convenient for me. So why n plus 1 is the size of our my cache? Size of my cache because I'm calculating the nth Fibonacci number. For that I need at least nth index. So that's why n plus 1. And why minus 1? Minus 1 because none of my Fibonacci number, any of my Fibonacci number cannot be minus 1, right? It starts with 0, 0, 1, 1, 2, and so on. So minus 1 represent that my cache is empty, that slot is empty. I have to calculate it. If it is not minus 1, which means something is stored which I've stored that stored my result in my past. Then, as I said, it's a recursive function. So fib of n initially, at first, we handle our base cases, the cases which cannot be broken any further, and from where we are returning back up. N equals to 0, return 0, n equals to 1, return 1. And there's an extra check after my base case where I said cache check. Okay, where we are checking if DP of my current state, for example, DP of n means nth Fibonacci is not minus one, which means in past I have calculated it, so I will simply return it. And if it is equals to minus one, then I will proceed further and solve my problem. I guess you know this recurrence relation. It's been already taught in the morning. In nth fib of n will simply call fib of n minus one and fib of n minus one. Whatever is uh, returned, I will simply return that only. But before returning, I am storing that result in my cache dp of n, which means I have calculated the state and it is stored in my dp of n. So in future, for example, dp of 5 with fifth Fibonacci number is already calculated and stored. So in future, in that tree, I again jump back to fib of 5. So instead of calling fib of 3 and fib of 4 again, I will simply check the cache whether it is present or not. And I'm pretty sure if I've already calculated, then it won't be minus 1. And I will simply return from there in constant time. Okay. And the final is answer extraction. See out fib of n. So that's the problem statement which you already know. We can say what the zeroth Fibonacci is 0, 1 is 1, and for n greater than equals to 2, this recurrence relation holds. Yeah, you can see. I think you already know this. This is the recursion tree I was talking about. It was also taught in the morning, but still I'm giving you brush up again. See, here I am calling n equals to 6, which means I want my answer the sixth Fibonacci number. So sixth Fibonacci number will call simply f of n minus 1 and f of n minus 2, which means f of 5 then f of 4. As you can see here, fib of n calls 5 and 4. 5 calls 4, 3, 4, 4 simply calls 3, 2, and it goes like this. 5 is called, then 4, then 3, then 2, then 1, then backtrack to 2 again, then 0 is called. So 2 is already being calculated and it is returned to 2, then 1 is called. So in this way, this tree of root equals to 3 is calculated, then again I'm backtracking back to 4. 4 is again column 2 and 2 is again being calculated. You can see over 3 over here. Similarly, once 4 is calculated, the fourth Fibonacci number, which is 3, is calculated using this tree. So many function calls, right? Then again I return to 5, then 6 again calls 4 and this tree is again formed. This is the reason why my time complexity rises to exponential 2 power n roughly. So, but after using DP, what happens is once this 4 is calculated, this node I'm talking about, once this 4 is calculated, it is already stored in my cache. So again, when 6 call f of n minus 2, f of 4, I simply check my cache whether dp of 4 exists or not, if it is minus 1 or not. If it is not minus 1, which means I've already stored 3 over here, I will simply return 3 instead of calling f of 3 and 2 again. So, so my tree becomes like a linked list. 6 called 5, 5 called 4, 5 called 3, 3 called 2, 2 then base cases will be returned and then simply 3, 4, 5, 6. So instead of a tree, a linked list is formed. It's working like a stack. एक के ऊपर एक. Then that's the code. It's pretty understandable, but just two things are extra over here that I'm carrying a my cache vector in DP with reference, and before calling my further subproblem f of n minus 1 f of n minus 2, I'm keeping a check, cache check, whether this state is already being calculated or not. If it is not, then already computed and return. If it is not computed, then I will call the recursive functions smaller problems, and whatever is returned, I will store that value in my cache, so that in future, if again the same state is called, for example, f of 5 is calculated, if f of 5 is calculated again, this if condition will be true at that time, and I will simply return whatever the fifth Fibonacci number is. So this function calculate the 10th Fibonacci number, and this is my cache. It will be storing all the Fibonacci numbers, and this is the cout function will be which will return fib of n. So as I said, time complexity will be linear in n because each state is called just once, not twice. Even it is called twice, I'm simply returning using this if condition in constant time. So that state is not calculated again. And stack space, why stack space is linear? Can anyone tell? Yeah, space. Why the space is n? Yeah, this DP is uh, storing linear space, but why I'm talking about auxiliary stack space. What's that? Can anyone say?
In
Well,
recursion, in the stack, we call the function like while calculating f of n, we are already storing f of n minus 1 in our stack and then calling f of n minus 1 for that too. So the recursive stack space is utilized there.
Okay, okay. Uh, Anyone else was also trying to speak something? I guess not. So yeah, he was correct. Basically, every time I'm calling a function, recursion. So I was saying, every time if there's a recursive stack is created. For example, f of 5 calls f of 4, then CPU switches to that function, and that the so basically a stack is formed one over another. So at max, when f of n is called, f of 10 is called, f of 10 called, f of 9, 8. Similarly, it goes till f of 0, and again it backtracks downwards. So in this way, auxiliary stack is created. And on top of that, I'm also using this cache, so this is also taking some linear space. This is a pretty famous problem, 0 1 knapsack. Anyone have any kind of idea about this problem? Have you seen this before? It's pretty famous.
Yes.
Bolo?
Mainly in knapsack problems, we have a condition on the basis of which we have the choice to go ahead, means take a decision or not take a decision. That is why it is 0 and 1. And we have at times a capacity that we will stop taking once that capacity is reached, or that condition is based on the capacity. That maybe if it is the thing we are choosing, suppose the value that is less than the capacity, then we can take it. Otherwise, we will continue that way.
Yeah, right. Anyone else? Okay, then. So here, what are we trying to find is, here we are given two arrays vector whatever. One is value, another is weight, and one is capital W, which represent total weight. So you have to pick items, zeroth, one, second, and with every item it has a weight and its corresponding value. For example, the first item is weight is 10 and value 60. This item 20, its weight and value is 100. Similarly, the last item, the weight is 30 and value is 120. So you have to pick the items and maximize your value. What's stopping you doing that? It's a total weight, your knapsack capacity, which is just 50, which means you can whatever items you are picking up, the sum of its weight should not exceed capital W. You're getting it, and there is only one item of each type. So if your weight is 50 over here, then it's pretty sure you cannot pick all the items. You can pick two at max. Yeah, any combination you can pick just two values. So greedily you can think that okay, the value is 50. I will take this one 120 and 100. So 220 will be my answer, and total weight I'm picking is less than equal to 50. Right. And for the second case also, sorry, for the second case also here value is 10. So in this case, okay, the explanation is given. Anyways, so values, then how are we maximizing our weight here? By picking the weight 4 and 3, that is 40 and 50, the two maximum value elements, and the weight over here is 7, which is less than my knapsack capacity, so I can pick. So the maximum value which I can return is 90. Why it is dynamic program, problem, but not a greedy problem? Can anyone explain? Like I can simply sort the values according to a value and pick the elements from front, right? That I can do. What's stopping me doing that? Can anyone explain?
Because there
The
is
condition
huh,
the condition of the weights which is being given, there can be a test case where those I mean the fact of that weights can be exploited, and it could lead to an n square solution if we use a greedy approach.
also we can tell one thing, that there is no linear relation between the values and weights. Means how the values, the weights are related to its value, there is no linear relation. So you cannot just simply sort and use greedy to get the optimal.
Yeah. So as we said, there is no relation between weight and value, which means the only thing I'm left is trying all the combinations. So that I'm trying all the combination, and whatever gives me the maximum value, I will simply return that. Okay. So if I do that, can anyone just think what could be my time complexity if I do that? Like every value I have two options, whether to pick it and not to pick it. Then what will be my expected time complexity roughly? Hey, are you all thinking or should I explain? Okay. So the answer to my question is 2 power n, because every index I have having two choices, whether to pick it and not to pick it. A binary tree will be formed if you can visualize. A binary tree will be formed, and my time complexity will go to 2 power n. And if that's the case, I cannot handle any case with n, the size of the array greater than equals to 20. Okay, 20 or 25 something. So let's see that code first. Then I will say you how to memorize it. That Suraj told right. Okay, every index have two condition, two checks whether to take it or not pick it. This is the function. So at every index, I'm going for top to bottom. For example, if this what's my state? Initially, I have to issue what's the state. So this function represent if I'm standing at anything, the ith index ind, and with my leftover capacity capital W. With this index and with this capacity capital W, what is the maximum value I can collect from the array? This is my state function. And what's my base case? If the index goes well below zero, which means all the items are finished, or my weight is over, which means my knapsack is full. So at that case, I will simply return zero over here because I have no items left, or even if the items are left, I have no more capacity. But if that's not the case, I have two options. Either to not take it. If I don't take it, I will go to the lower index, and my capacity of the bag will be same, capital W. But other case, I can take it. When I can take it, if the value of that, the weight of that particular item is less than my capacity left. If that's so, I will add my the value of that item to my taken initially as zero. I will add that value to taken and again make a recursive call of lower index with lower weight because the item was only one, right? If I have taken it, it's no more. I have to go to lower index, and the also my knapsack's capacity will be reduced by weight of that one, that item. And when I'm returning over here, backtracking over here, then I will simply return the maximum of those taken and not taken. So in this way, my answer is computed using recursion. But the problem with this is, as I explained, the time complexity goes to 2 power n, and the space is only linear only because there are just n indexes. So here only I will use my dynamic programming and introduce a cache which will be storing my states. It's the same code by the way. Just few lines are added. One cache check and one I'm storing the value in my cache. So here I'm using a 2D vector. You can also use a 2D matrix, I mean array. The dimensions are n and w plus 1 because for each state the maximum index I can have is n minus 1. So n indexes are required and weight w the maximum weight plus 1 because if I need the capital W weight, I need at least my size should be W plus 1 and minus 1 is the represent that this state isn't calculated yet. So I have to calculate that. The base case is same. One cache check is added whether this state is already calculated or not, which means at this index with this capacity, I have calculated or not. If if it is equals to minus one, which means I have to proceed further. And if it is not minus one, I can simply return the state, which is already calculated. And again, the not taken and taken call is made. And before returning, I'm simply storing the state's value in my cache. So in future, if I return to the same state. So instead of doing redundant work, I will return using this cache chain. So in this way, I am trimming my time complexity to 2 power n, which is exponential to polynomial, which is now n order of n square, or you can, to be more precise, I will say is n into capital W. N is the size of the vector and W is the capacity. Because each state is calculated just once, unlike before where again and again because a huge recursive tree will be formed. Here only it will be the states will be called like linked list. Okay. So time complexity will be n into capital W and space will be n into capital W because of my cache. This 2D vector n into capital W. And big of n because of my auxiliary stack space. So further PPT will be explained by Ayush Anand. Thank you everyone. Or is anyone having any kind of doubt or question? You can ask. Okay.
Hello everyone, am I audible?
Yes.
Am I audible? Okay, fine. Just a second. Okay, so is my screen visible? Is my screen visible?
Yes.
Okay. So now we'll be starting with the first part, subsequence DP. So can anyone tell me what is subsequence? What is a subsequence? Hmm. Okay, so you all know the definition of subsequence, right? Hello.
Yes, we are like it can be random items, but in the sequence of the array.
Yes, right. These are the elements of the array itself, but the order has to be relative to the array and any element can be there. So suppose 3, 10, 2, 1, 20. So 3, 10, 20 is a valid subsequence because these elements are present in the array and occur in their specific order. Whereas if I write 3, 1 and 2, it's not a subsequence because even if they occur in the array, they are not in the relative order. So now we'll be starting with the first question in the subsequence DP series, that is the longest increasing subsequence. So what is the task? Given an array ARR of size n, the task is to find the length of the longest increasing subsequence LIS. That is the longest possible subsequence in which the elements of the subsequence are sorted in increasing order. You can check the example once and try this question for a few minutes. After a few minutes, we'll be brushing up through the intuition of this question. Okay, so was anyone able to think anything regarding this question? Like, how can I approach? What should I do exactly?
Yes, we can try to find the longest increasing subsequence that is ending at a particular index and go on storing that. Suppose we reach at fourth index. Now we know the value at fourth index. We start traversing from the first index, and we suppose we see that up to second index the value is less than or equals to this our fourth index value that we are currently in. So we already have calculated what is the length of the longest increasing subsequence till second index. So we'll come and add 1 to that and store in the place of 4, and like this continue till the end. Now in the entire array that we are forming, result array, there we are getting the length of LIS for every index. Now we find the maximum among that, and that is the answer.
Yeah, right. So now, uh, how many of you were able to understand the 0, 1 knapsack problem? Probably, I think that everyone were able to understand the whole concept. So there were two things involved in the knapsack problem, if you would have observed, and that is the take and not take. So we'll be applying the very same logic over here. To understand in basic words, let me do one thing. Let me keep some two pointers over here, the previous pointer and the current pointer. The previous pointer currently points to the -1th index. So now what we can do is we'll be designing a recursive function over here, because iteratively doing this is not possible. So we'll be designing a recursive function as of now. So now we can see that current pointer points to 3, and as of now there is no element behind it to take as a reference. So can I consider 3? Anyone answer? Can I consider 3?
Yes, as it is the first one, so we can consider.
Okay, so it is the first one, so I can always consider this. Now, if 3 is considered, then obviously my previous pointer moves here and the current pointer goes here, right?
Yes.
But there could have been one more case that if I would have kept the previous pointer intact, current pointer would have been here itself. But I am skipping 3. I'm not interested in taking 3. I want to take 2. So that can also be done. A provision can be kept to increase the current pointer in case if I do not want to take this, right?
Yes.
Okay, so currently we think that we have taken 3. So if we have taken 3, then what happens? The previous pointer shifts to the place of the current pointer, and the current pointer comes to the place of the very next index. Now we'll be checking through the previous index. Now we have something on the previous index which acts as a reference of considering the current index. So now should we consider 2?
No, we cannot consider.
We cannot consider 2 because it is lesser than the previous index. So as usual, we'll be applying the not take case and the pointer moves forward. Can we consider 10 now?
Yes, we can consider.
Okay. So now what happens? The previous moves to 10, current moves to 1, right? So now can we consider 1?
No.
Okay. So again, it's a not take case. So current moves here. And now we are on 20. Can 20 be considered?
Yes.
Yes, 20 can be considered. So the previous pointer moves here and current pointer goes out of the bound, showing that we have got one possible result. When we design our base case, so if our current pointer exceeds the limit, that means we have designed one of the cases. Let's consider one more case. Suppose if I keep my previous pointer here, but it's my wish, I'll skip 3, I'll go to 2, and I can always do that. So 2 can be considered because it's just the first element of the array. Am I audible? And am I correct on this? 2 can be
Yes.
considered. Okay, so the previous pointer moves here. The current pointer moves here. Now tell me, can 10 be considered?
Yes.
Exactly, 10 can be considered. Now if 10 is considered, previous pointer comes here and the current pointer goes here, right? Now tell if 1 can be considered or not.
No.
No.
Obviously no. So again, the current pointer only moves to the next index, right? Now can 20 be considered?
Yes.
Yes. See, we got one more possibility. So why are we designing a recursive code? Because recursive code helps us to get almost all the possibilities which we want in case of finding all the required subsequences. Now, how to consider the maximum case? So now we do one thing, we design a recursive function based on the previous index and the current index. Here we'll be writing the base case. On that we will be coming later on. Let's design. Now, if we are suppose taking a particular index, we are taking this element, then currently take is assigned to 0. So what would be the case for take? There's an if condition if I have to write over here. If I have to give the if statement for considering a value in take, then what would be the if condition right here?
ARR of current should be greater than ARR of previous.
Okay, ARR of C should be greater than ARR of B. But I think we are missing out on something.
Yes, and current and previous both are in means current is less than n. Oh
No, no,
yes, yes,
it's
yes.
okay.
Mhm.
We are missing out this, that suppose if we have to consider only one element, our current array is empty and we have to consider one element, then what we do? We have to take this condition. So now what I can do is, take can be considered as, that means I have added one. That means one element has been added in my array. So can I say that if I have an array till, and if this is the current index, till this point the problem is solved. Till now the problem has been solved. If I'm considering the current index, that means till this index I am solving a problem.
Yes.
So what is left out? This chunk of the problem.
Yes.
So now how to solve this chunk of problem? What should I write after the plus, which returns the result of this chunk?
Oh yeah, why did we do p equal to minus one, or like how does
f
it
of f
help
of
with
p comma c
in
plus 1.
Okay, p equal to minus 1, because at first we were considering the current pointer at index 0. Current pointer was being considered here and previous pointer was being
okay,
considered
like
at minus 1, indicating that at this point of time there is no previous element. So if previous is minus 1, then obviously I have to choose only one element as of now. So I can always consider any of them. Any of them can be considered. So previous gets shifted to that particular point and the current gets shifted to previous plus one. Sorry, current plus one. So is it clear?
yes, ma'am.
Okay. So can I say that f of p comma c? So what comes at p?
C C
C comma c
C
plus
plus
1,
1.
correct? So this is my take condition. Not take, what will I do? What will I do for not take?
1 plus f of p comma c plus 1.
0 plus, not
Why
0
minus.
will I
plus.
consider
0
one?
plus.
0 plus.
0
Yes,
plus.
right. P would be intact as it is. I'm not moving P. I move the current pointer instead.
Yes.
Just a second. Okay, sorry for the glitch. So now, if I have my cases ready, so now there'll be a return by this function. What would be the return ultimately? What would be the return from this function? If I want the combined answer, the length of the longest increasing subsequence, then what will be the return from this function?
Max of take comma not take.
Exactly. Max of take comma not take, right? And hence the function ends. But we are missing out on something, the base case. So what could be the base case?
When the current pointer is out of bounds.
Yes, right. If the current pointer, let me consider the length of the array is n. If current pointer goes out of bounds, then simply return a 0. That means in on the other side, I have no problem to solve, or I'm getting a 0 as a return response from the other side. So now when the recursive call comes back, so it will correspondingly solve all my problems. But now there is a catch here regarding the time complexity, and it's going to be of exponential time, right or wrong?
Yes.
So now what can I do for an optimization so that my complexity falls down to O of n square? O of n square, yes.
Memorization.
Yes, right,
Memoization.
memoization. Okay, so now how will I memorize the code? So what I'll do, I'll make an outer DP table over here, which would be of the
N plus
dimensions
1.
n plus 1, comma n plus 1. It's okay, you can take up till n also. I'm just considering a bit of extra space over here. So now I'll have to add some line over here. What would be that line?
If dp of p comma c is not equals to -1, then return dp of p comma c.
Yes. If dp of p comma c is not equal to -1, then I'll call a return of this very thing here itself. Why? Because if it is not equal to -1, that means this problem has been solved somewhere in the recursive tree. So the thing which increases my time complexity in recursion is actually recursing deep down into the tree. When I already have a problem solved, then why should I recurse deep down into the tree? So if I have the problem solved, I take the result from my table and I return that itself. And how to store intermediate results? So dp of p comma c is equal to nothing but max of t comma nt. So is this clear?
Yes, yes.
So longest increasing subsequence is clear. So you can look through the code once that what exactly has been done over here to get a clear idea. If you have any doubts, you can ask. It's the exact same code which I have explained right out there. And just make sure when you're writing previous index, so you write previous index plus 1, because the starting initialization of previous index starts from -1, and -1 is an invalid index in any table. So just make sure that when you're storing, you store the plus, you make it +1 and store the result. So is it clear?
Yes.
Okay, so are you all getting an idea now how is it done? Okay, so now the thing is time complexity is O of n square now. And space complexity is also O of n square. But this is a bit of hefty approach still. Can anyone tell why? Still a bit of hefty approach.
Because of the recursion overhead calls.
Yes, right. Because of recursion overhead calls, what happens? It adds to an extra O of n square time complexity. So that is not really good. So how can I eliminate that case of that extra O of n square space complexity?
By tabulation.
By tabulation.
Okay, okay, tabulation. So now how will you do tabulation? Can anyone give an idea regarding this? Now you have the memoization code in front of you. So now the best thing you can do is to tabulate it.
Yes, we would just run two for loops for the index and the previous index.
Okay, yes, right. We can run two for loops for the index. At first, you'll be initializing the base case. This base case needs to be initialized, and also make sure that when you're running the loop for previous index, so you run it for previous index plus 1 instead, because you need to make sure that -1 is never coming as any index, otherwise it will give errors in your code. You can check the tabulation. Okay, sorry, tabulation code is something which I'll be assigning as a homework. You people will have to try it out on your own. Try to make it out from this recurrence relation itself. Okay, now one question I have. Is there any more optimization possible in LIS? Can I find LIS with certain more optimizations? The basic time complexity for LIS is n square. Can I bring it down? Am I audible?
Yes, yes.
Okay, so can anyone suggest that how can I bring it down?
Mm, a binary search.
Okay, right. We can use binary search here. What exactly in binary search do we have to use? Okay, so I'll get this clear. We have to use the bounds wala concept over here.
Found an upper bound.
So let me write this 3, 2, 10, 1, and 20. Suppose currently if I have an empty array with me, consider this to be temp. So now as there is nothing in the array, so I can plug in 3 over here, right or wrong? I'll be doing a single traversal on this main array. And if there is nothing in the array, can I plug 3? Hello?
Yeah, yeah.
Yes.
Yes, yes.
Okay. Now comes 2. Where can I exactly plug in 2 into the array?
When the last value we have stored is less than 2.
Yes,
The
right.
last value we have stored is
Okay.
3.
Okay.
So
So
we
now that's where the lower bound function comes into the play. What lower bound means, either the exact element or an element just greater than it is found in the array. So lower bound of 2 over here is nothing but 3. And 3 comes at which index? 0. So instead of 3 here, I'll be placing 2. Right? Hello?
yeah, yes.
Okay. Now where will 10 come? Just after 2, because it is greater than the end element. So
Yes.
10 comes up here. Now 1.
1.
Where will 1 come?
At the first index,
Yes, right. Instead of 2, 1 comes up here because of the lower bound which we are
found of 1
applying.
is now, yes.
And now comes 20 directly because it is greater than the end element. So what is the end length over here? Length of the array? 3.
3.
Right? So this was the length of my alias, right or wrong?
Yes,
Okay, so this method is feasible only to find the length of the LIS, right?
yes.
But the array which I am obtaining, is it the actual LIS?
No,
No, correct. Because over here, the elements are not in their relative order and they are just present in the in a sorted order in the temp array. So the length gives the exact justification for LIS, but the array itself is not the LIS. Hope that's clear from my side.
yes, yes.
So you can go through the code once. And if you have any doubts, you can ask. Is it clear?
Yes.
Yes.
Okay. So now the next question is DP on subsequences. Longest common subsequence. So given two strings S1 and S2, the task is to find the length of the longest common subsequence. If there is no common subsequence, return 0. Okay, so now what does this question say? Let me take one example from here itself. ABC, ACD. So what does longest common subsequence actually mean here? The length of the longest subsequence which is common in both of them. Exactly.
Yes.
So what will be the case over here? What is the longest common subsequence here?
Either A or just C.
It's it's combined,
It's AC. Yes.
not either. It's combined.
Yeah.
Length is 2, it's combined. Okay, so the length is 2. So now we have to find the length of the longest common subsequence. So now apply your logic and tell me that how can we do this question? How can we make a recursive code here, then accordingly memorize, tabulate as per the needs? So if you are able to think of an intuition, please let me know.
Where first we'll define two pointers on the two strings,
Okay,
and then we'll just compare them.
okay, fine. I'll simply write two strings. Okay, so now we'll be going through the logic of this question. Now consider the I pointer is here and the J pointer is here, right? Okay, so now there is one case that if both of them are equal, then what can I do?
Then we have two choices, either take or not take.
Yeah.
If both of them are equal,
Yes, if they are equal, then we have two choices, either take or not take. And if they are unequal, then we will not take it.
okay, if both the characters are equal, then obviously I'll take and move both the pointers behind.
Yes. We have only one choice if they are equal.
Yes, only one choice is there that you have to move both the pointers behind.
Yes. I minus
But
one.
now, in case if they are not equal, then what can I do?
There will be two more recursion calls, one with pointer I and j minus 1, and another one will be I minus 1 and then j.
And then we'll take the maximum of the two.
Exactly right. So I minus 1 and j j minus 1 will become the two choices which we'll be considering if they do not match. So let's design the function accordingly now. Base case is something which I'll design later on. So currently take is 0, right? What will be the condition for take? Consider the two strings as s and t. If s of I is exactly equal to t of j, that means this is the only condition for take. Am I audible?
Yes. Yes.
Then take equal to 1 plus. Why 1 plus? Because we are considering this character in our subsequence. And what would be the left side of the problem now? We will be decreasing both the pointers from here, right?
Yes.
Not take. What will we be doing?
It will be 0 plus maximum of I minus 1 j and I j minus 1.
Yes. I minus 1 j and f of I j minus 1.
Yes.
Okay, so anyone has doubts in this part till now? In any part till now? Okay, fine. Then what would be the return of this function? Max of take comma not take again.
Yes.
Okay, so till now most of the part is done. Now the thing is we have to design the base case. How can we do that?
If any one of the index goes out of 1, less than 0
Yes.
basically.
Yes, right. If any one of the index collapses, direct the problem is solved, return 0. Okay, but now the problem is this code is of exponential complexity. How to optimize this?
Memorization.
Yes. I'll keep dp of n comma m as my table right out there. N is the size of string s and m is the size of string t. I'll be adding the required condition over here. If dp of ij is not equal to -1, then I'll simply return this because this problem has already been solved. Otherwise, what I'll be doing is dp of ij will be stored here, right? Once you can check the code for the same. And if you have any doubts, you can ask. Okay, so now your task, now another home task for you is to tabulate the very same code. And that tabulation will be really easy. I've kept the tabulation code over here for your reference. You can check it out once. It's the very same thing. First is the base case initialization over here. Whatever we were doing here till now, that if one particular index collapses, another still remain, so initialize them to 0. Now from 1 to n and 1 to m, I'll be running the indices and now I'll be checking that if they are equal, then I'll be taking the condition and I'll be going to the previous indices for both the cases. Or else what I'll do is I will decrease any one of them and consider the max of the two possibilities. And the final answer would be dp of n comma n. So is it clear? Am I audible?
Yes.
Fine. Okay, so now we'll go to the next module, that is dp on strings. So specifically now we'll be dealing with the string part. So now this question is edit distance, a very famous question. So given two strings s1 and s2 and below operations that can be performed on s1, the task is to find the minimum number of edits or operations to convert s1 into s2. So what are the operations? Insert. You can insert any character at any particular position in s1, remove a character in s1, or replace a character in s1, right? Suppose consider this example. Geek and Gisek. So now what are the number of operations required here? Considering all the cases, insert, delete and replace. Were you able to understand my question?
Yes, one.
No, it will be only one operation
Yeah, one.
because
One.
we have to do all the kind of dealing with this particular string, the very first string. Consider this as S1 and this as S2. All kinds of stuff would be done on S1, be it insert, delete, and replace. So the only operation which we'll be performing here is insertion of S between the two E's, right? Which gives us the target string. Okay, so now let's check that how can we write a code for this. Now let me consider two pointers from the end, I and j. Now my question is, if they are equal, that means no operation needs to be performed and I can simply take both the pointers behind. Right or wrong? Hello.
Yes, yes.
Hmm. So if S1 of I equal to S2 of j, then can I say that both pointers can be decremented? Fine. But now comes the, till here it's fine. But now it goes back here. J comes here and I comes here. So now what can I do over here? I have three operations: insert, delete and replace. If there is no match found.
Yes.
Yes. So what I need to perform here? The insert operation. Fine. So how can I do the insertion over here? So for insert, can I say that simply what I'll do is j pointer will be decremented. Am I right or wrong?
Yes.
Okay, so as the j pointer gets decremented, so j comes here. Now they are equal. Again, they go behind, and if they fall below zero, then that comes as the base case, but not exactly. Now comes another question. If I am deleting a character or removing a character, then what am I doing exactly? Am I decrementing the ith pointer? Because consider this example. Till here it was fine, but now it came over here. So what will I do over here? Simply I have to delete. How can I delete? Simply I decrement the ith pointer. Right or wrong?
Yes.
Clear to others?
Yes.
Fine. Okay, so now tell me what is the case for replace? If there is no match and if I have to replace, then what is the case?
I minus 1 and J minus 1 both.
Yes, both will be considered again. Fine. So now we'll be writing the code again. Base case would be written here. So now what is the I'm keeping this as a very high number because we have to consider the minimum. So now what is the condition for take? What was the condition for take?
Both the characters were equal.
If S1 of I equal to S2 of J, then take was simply that there will be no operations performed and I'll be decrementing both the pointers. Now comes the case of not take. What would that be?
It would be 1 plus minimum of all the three operations like insert,
Yes.
place, and delete.
Yes, 1 plus minimum of f of I minus 1 j, which was remove f of I j minus 1, which was insert, and f of I minus 1 and j minus 1. And what would be the return from this function? Minimum of take and not take again.
Yes, yes, yes.
Fine. But now what's the most interesting thing here is the formulation of the base case. What could be the possible base case for this?
Either I becomes 0 or J becomes 0.
Okay, okay. If I goes less than 0 and if j goes less than 0. But now the thing is, what would be the return values in both cases?
In case of I less than 0, it means the first string got exhausted, so the remaining characters of the other string would have to be, I
Yes,
mean, they have the
yes,
only option
right.
to get deleted, so return J.
Yes, right. You have to return j plus 1. Consider j plus 1 as the number of operations, considering that it's a zero-based indexing. So, if my ith pointer is exhausted, but now a few characters are still considered after the before the jth pointer. So now the number of operations to delete them would be nothing but j plus 1. Now similarly, what happens if j goes less than 0? If j goes less than 0 and something is still there behind the ith pointer, that means what am I supposed to do? Return I plus 1 as the number of operations needed to be performed. So this is my whole recurrence relation for the thing. Now, how to optimize this? Again, dp of n comma m, and you'll have to write the dp of ij not equal to -1 case here. If it's not -1, that means the problem has already been solved before, and now we can give the return value as this very thing itself. Otherwise, dp of ij is nothing but this. So, is it clear till now?
Yes,
Fine.
Yes.
Okay, so now I'll be showing the code for this. You can check the code and tell if you have any doubts or not. So, is this code clear? Hello?
Yes, very clear.
Okay. So now for the same thing, we can see that how are we tabulating this. So this is the edge case that suppose if J collapses, so I still has some things in it, so I have to initialize with I over here. Similarly, if I collapses, then J will have to be initialized accordingly. Now we'll be running a double loop and checking if they are same. Then obviously no operations will be performed and I directly decrement both the indices. Else, an operation is being performed and minimum of the three cases is being considered. So once you all check this code and let me know if you have any doubts. Is it clear? Hello?
yes.
Yes.
Fine. Now let's go to the next question. Longest common substring and an addition to longest common subsequence now. Now you have given two strings str1 and str2. Find the length of the longest common substring. So let me consider this very example. Can anyone tell what is the longest common substring here?
AB.
AB, right? So length would be 2, right? Hello. Okay. So now, how can I approach this problem? Any ideas in your mind? How can I approach this problem? Okay. Can I say that I can consider two pointers here, I and j again? Till the time they are matching, there is no problem. The moment they stop matching, then what am I supposed to do? Till the time they match, I will decrement the indices. But what happens if they don't match? Hello, am I audible?
Yes.
Okay. So if they don't match, can I say that whatever counter I had with me, I reset that to 0. In some maximum counter, I will store the previously counted value. Suppose here it was 1 and the mismatch came right out here. So can I say that count will be 0, max count will be 1 till now? Again, the mismatch comes here. So the count still remains 0 and the max still remains 1. But now there's a match here. So I'll be incrementing it by 1. Same, the match comes here. I'll be incrementing it by 1. Right?
Hmm. Yes.
And now, as I have no indices to cover, then I can simply update the max with the maximum value, right? So now can I say that a previously written tabulation code for the LCS can ultimately help us crack this question? Let's go to the code and understand this, that how we are doing. So till here, it was completely fine. Now, as soon as my characters match, can I say that both pointers will be decremented? What does plus 1 mean? That I'm considering the characters in my substring. Then dp of ij, I'll be storing this value. This very value will be stored in dp of ij. And answer will be nothing but max of the current answer which you are having and the current counter value which you are having. Otherwise, if there is no match found, so can I say dp of ij will be set immediately to 0? That means I'm stopping the count. The substring length becomes 0 as no character is matching. So is this question clear? Hello?
Yes.
Everyone, you have any doubts? Is it clear to everyone?
Yes, sir. Yeah.
Okay. So we're able to understand this particular part, right? That if the match is found, then I'm decrementing the indices right out here. I'm storing the value over here, and the answer is being considered as max of all possibilities. Otherwise, if there is no match found, then I'm immediately setting that part to 0, stating that now my count will be starting again. So the overall complexity would be quadratic, that means O of n cross m, and same goes for the space complexity. Okay, so by this lecture you would have understood substring and subsequence DP, and majorly would have understood that in subsequence DP, the major case is of take or not take. Either I take the particular index or I don't take them. So now my one question comes up. I hope that DP dimensions are clear. That what do you mean by 1D, 2D, 3D DP, and so on. So 1D DP means that whatever is my recursive function, there is only one changing parameter over there. 2D DP means there are two changing parameters, as we saw in the last few cases such as LIS and LCS and the 0-1 knapsack problem. But in case of Fibonacci factorial, it's a 1D DP case. Now 3D DP, there are many cases of 3D DP as well, where you can have three changing parameters and hence it's a 3D DP. And most of you would have given a recode in your summer break, so you would have seen the question F. The question F was based on DP. Now there are two ways to solve it using DP itself. Either it's a 10-dimensional DP, or in case if you know bitmask DP. Bitmask DP में it is brought down to almost 2 dimensionals. But in case of normal DP, if you are applying it from scratch, then it's 10D DP. So you all can try that question once from the recode which you gave in your summer break. The question was on DP. So I hope this part is clear. That what do you mean? What do you exactly mean by the dimensions over here? Is it clear?
Yes.
Okay, so by this we come to the end of today's session. If you have any doubts, you can ask. Mm. Anyone has any doubts? If you don't have any doubts, you may leave.
Thank you.